We'll do the standard 3-minute grace period thing. That seemed to work okay before. By the way, apologies in advance if I'm a little bit frazzled. I've just been in back-to-back project meetings for the last several hours and they all overran. And I may also eat conspicuously during this lecture. So this is like the height of professionalism. Okay, let me try doing screen sharing. Do that. We get to see Mark. Okay, so seeing as though we didn't quite get the opportunity to finish discussing relativistic stuff last time, I'm going to just quickly take you through the last of what I wanted to say about the GR derivation and about things related to cosmology. By the way, sorry, for those of you who were worried, I know this lecture is scheduled for 2.5 hours. That's just to ensure that we had a bit of a buffer. Don't worry, I have no intention of speaking for 2.5 hours. I will finish probably quite early so we can all take a break, not least because I desperately need one. But hopefully we'll be able to cover at least some quantum mechanics today. Anything we don't cover today, we can cover tomorrow. Yeah, don't be concerned. Okay, so going back to the derivation I gave this morning, I kind of mentioned, or I alluded to the fact that this derivation of the continuum Einstein equations from kind of discrete causal network dynamics is somewhat analogous to, in fact, the ergodicity assumption we made is directly analogous to the derivation of continuum fluid dynamics, the derivation of the continuum Navier-Stokes equations from discrete underlying molecular dynamics. You know, the same ergodicity, the same molecular chaos assumption has to be made in both cases. And actually, mathematically, what we're doing is essentially the same procedure. So for those of you who don't know about that derivation, and by the way, I should say I'm not claiming to be an expert on it either, but to the extent that I understand it, the basic idea in that derivation is you start from a one-particle distribution function for some collection of molecules, you construct the associated Boltzmann equation, and then you introduce this parameter epsilon. So on the right-hand side of the Boltzmann equation, where you, in front of the integral operator for the interparticle collisions, you have this 1 over epsilon thing appearing. And then the idea is to just take to take the distribution function and expand as a formal power series in small powers of epsilon. And so what that translates to ultimately in the hydrodynamic case is like a kind of tensor power series expansion. So what happens is if you take the 0th order term with respect to epsilon, you get a Boltzmann equation that yields the Euler equations, which are the sort of dissipation-free versions of fluid mechanics, the general dissipation-free statements of conservation of mass, momentum, and energy. And then if you go to a higher order, terms, if you take the 1st order term and so on, then you get the full Navier-Stokes equations with dissipation. And then there's nothing actually to stop you from going further. In fact, I mean, various people, including Stephen, using sort of cellular Thomson models of molecular dynamics, have gone about deriving higher order extensions to sort of hydrodynamics. So if you go to the next level up, the 2nd order solution, that yields this thing called the Burnett equations. If you go to the third order, you get the super Burnett equations and so on. There are all of these sort of higher order supersets of Navier-Stokes that one can consider. Now, essentially what we're doing is exactly the same as you know, in the relativistic case as one does in fluid mechanics, because if you run through the mathematical argument for the hydrodynamic derivation, what's going on is you're taking the total viscous stress tensor, that is the, you know, the tensor that describes the total stress that's attributed to strain rate in the fluid or whatever, in this idealized fluid. And then you're saying we can take this tensor and we can decompose it into a sum of a trace-free part, and a trace part, right? And so then the trace part, which is some scalar multiple of the identity tensor, manifests as a bulk hydrostatic pressure, and then the trace-free part manifests as the viscous shear stress. So that's the you know, the stresses that are not hydrostatic, but rather have some shear component to them. And that's exactly what we're doing in this relativity derivation. Effectively, implicitly, what we did by essentially doing this power series expansion, which is like a Chapman-Enskog expansion for the dimension and the curvature of the causal network, is we were taking the total Riemann curvature tensor and we were decomposing that into a sum of a trace part and a trace-free part. In our particular case, the trace part, which is some scalar multiple of a linear combination of identity tensors of effectively Kronecker deltas, that's the Ricci curvature tensor. That's the thing that we were using, which is kind of the 0th order term in order to describe the growth rates of the causal network. But then there are also higher order terms which come from the trace-free part. And in the context of the Einstein equations, the trace-free part of the Riemann curvature is what's called the Weil curvature tensor. And so the important thing to note is the ordinary Einstein field equations they only place constraints on the Ricci curvature and they leave the Weil curvature unconstrained. And that fact actually has a bunch of implications for things like gravitational waves and other things like that. And so the exciting thing is that because we have an effectively hydrodynamic procedure based on this kind of space-time averaging of dynamics across the whole causal network, we have this hydrodynamic procedure of deriving the Einstein equations. We also have a way of accessing and probing these higher order terms, effectively like the analogs of the Navier-Stokes Burnett super Burnett equations, but for relativity. And so in particular, you know, we only considered growth rate with respect to the second order contribution, but we could have considered growth rates with respect to the higher order contributions as well, which would have placed constraints on the Weil curvature. And so the sort of geometrical picture of what's going on there is when we place constraints on the Ricci curvature, they're effectively like divergence constraints. They're saying that there are certain conditions on how the volume of a geodesic bundle in the causal network is able to grow. And in fact, so in the vacuum case, it's saying that it's not allowed to grow. It has to, that the volume of a geodesic bundle has to remain constant, because if it doesn't remain constant, if it grows, if the geodesic bundle is allowed to have a kind of monotonically increasing volume, then that will correspond to a causal network that won't limit to a finite dimensional space. And so, but now we also have a way of potentially deriving constraints for the Weil curvature, right? And so now this is a more fine-grained description of what's actually going on in space-time, where we're saying there aren't just constraints on the volumes of the geodesic bundles, but actually on their shapes, almost like we're kind of driving, I don't know, higher harmonics on geodesic bundles, something like that. So this is something that people have considered in ordinary general relativity. There exist higher order analogs of the Einstein equations like Lovelock gravity that works in higher dimensions, that uses these higher order corrections or higher order contractions of the Riemann curvature, I should say, which therefore do place constraints on things like the Weil curvature. But things like Lovelock gravity have been explored for kind of mathematical interest only. We potentially have a way of actually deriving these kind of theories actually from first principles. And I believe Cameron's project is related to attempting to do at least a kind of toy version of this, to see if, at least in certain small cases, we are able to derive effectively higher order corrections to the Einstein equation, where we're even just kind of phenomenologically, we should be able to see what kind of constraints exist on the shapes of geodesic bundles that are permitted in the causal network. I'm kind of excited to see how that project ends up going. So one of the reasons why this is kind of interesting is sort of what I'm not yet. Okay, this is, I should be completely upfront about this. This is a conjecture that sort of Stephen made that I'm still not completely convinced of, although it's certainly an interesting idea. But Stephen's sort of idea was that these higher order corrections might be related to dark matter. that somehow, you know, that they might constitute, it might be the case that the ordinary Einstein field equations that just constrain the Ricci curvature, you know, those might be a good approximation for small, you know, for relatively small scale problems. But once you reach kind of galactic and intergalactic scales, you know, these higher order corrections might become more important, and you know, that might have implications for things like galactic halos and galactic rotation curves and things like that. That's an interesting question. We don't really know the answer, but it's a possibility that it's possible that it might be related to these sort of modified Newtonian dynamic models of things like dark matter and dark energy. That's certainly one possibility. So one thing that you might have noticed in this derivation is that we've essentially been assuming, I mean, as I've kind of kept mentioning, that we've assumed that there's some limiting process to a finite dimensional manifold. There's some limiting process where the causal network becomes finite dimensional. But there's actually, you know, when you have a network which not only does it not have a geometry defined on it, it doesn't even have a fixed topology. Unlike in ordinary differential geometry, there's no reason for you to assume that the dimension is not also changing. That's not something that one usually considers in differential geometry, for the simple reason that, you know, one of the axioms of a manifold is that the connected component, that you know, effectively dimension is a local invariance. So all of the connected components of the manifold have to have constant local dimension, have to have equal local dimension. You can't have connected components for which the dimension varies. But in our models, that condition is no longer necessarily the case. So in doing this Einstein field equation derivation, we kind of cheated a little bit by assuming that n was fixed and assuming that r, the Ricci scalar, was the thing that was varying. But we could just as equally have assumed that r was fixed and that n was varying. And, you know, and effectively, so instead of having a second order correction to n, we would be dealing with some exponential correction to n. And so, you know, something that would, a small change in dimension locally is kind of indistinguishable from a large change in curvature. You know, you know, it's just that one is affecting n in an exponential way, one is affecting n in a quadratic way. And so it leads to this interesting possibility that maybe there's a way of formulating general relativity that works for kind of manifold-like structures, but where the dimension is allowed to vary both locally and globally. And so that's something, again, we don't really know the right mathematical framework for thinking about that. I've made a couple of conjectures about a possible way of formulating it, but it's certainly not worked out in any detail. You know, because this is a purely conjectural thing, I'm not going to talk about it too much, but my basic idea is, in sort of ordinary differential geometry, you have this notion of a coordinate chart that's this homeomorphic map from open subsets in the manifold to open subsets in Euclidean space, and then curvature is then and so the manifold into coordinate charts is the connection lines, and then curvature is some measure of the degree to which the connection fails to be exact. And my basic idea was that maybe instead of thinking about coordinate charts, you could think about this more general kind of morphism, which is the thing called a covering map in algebraic topology. That's some smooth surjection between a topological space X and what's called a covering space C, which under certain conditions becomes this thing called a universal covering space. And then my idea was, if you consider X to be like the base space, which is some sort of manifold, some grid-like manifold-like structure with fixed dimension, and where, you know, and where C, the covering space, is the hypergraph you're kind of considering, then you could imagine, instead of having you would have this generalized notion of a connection, where instead of a coordinate chart, you would have something like a universal covering map. And then, rather than thinking about curvature as being a measure of the degree to which the connection fails to be exact, you're talking about sort of a kind of dimensional curvature, where it's measuring the degree of discrepancy between, you know, a point locally in the space that you're analyzing and the corresponding point in this space of homogeneous dimension. And so it's a way of locally characterizing the degree of kind of dimension discrepancy. But that's again, like I say, it's really just it's not something I've worked out in great detail. The particular reason that I thought that there might be a good approach for thinking about general relativity in variable dimensions is because of an analog to geometric group theory. So, in geometric group theory, obviously you have this concept of Cayley graphs, Cayley graphs are a particular example of what are called vertex transitive graphs. So graphs where every point has essentially the same neighborhood structure. So here are examples of vertex transitive graphs that we can think of as being like the base spaces for describing variable dimensional GR, that they are like the base spaces of effectively fixed dimension. And then we're going to place something on top of the base space that can have varying dimension, and we're going to quantify it we're going to quantify its curvature in terms of the degree of discrepancy between the local dimension of the space we're analyzing and the global dimension of the actual base space. And so then, as I say, because Cayley graphs give you a way of constructing vertex transitive graphs, they give you a way of constructing these kinds of base spaces. I thought there must be a kind of general way of thinking about this local dimension change in terms of geometric group theory. And we at least know one very, very toy version of that, which is the case of the relationship between a beta lattice and its Cayley graph. For those of you who haven't sort of encountered things like Cayley graphs in group theory before, it's just a way of saying, if you have a graph that's kind of that's finitely presented, if you have a group that's finitely presented, you can associate to it a finite Cayley graph, where each vertex corresponds to an element, and each edge corresponds to an application of a generator to that element. So effectively, it's a combinatorial way of expressing the presentation of that group, the sets of generators and relations. And so then it's pretty trivial to see that they have to be vertex transitive, although the converse isn't necessarily true. The Peterson graph is an example of a graph that's vertex transitive but not Cayley. And then you can define this thing called a beta lattice, which is an infinite graph, a rooted tree, where every vertex has the same number of neighbors. So again, it's again a trivially vertex transitive object, where the sort of neighborhood structure is defined by this natural number, this thing called the coordination number. And the interesting thing about that is that the beta lattice is effectively up to a factor of 2 is the Cayley graph for the free group on the number of generators given by 1/2 of the coordination number. And so essentially you can think of any presentation of a group as being a surjective map from the free group on that number of generators back onto the original group. And this is essentially, so this is an idea that people study in geometric group theory. And this is the idea that I kind of basically want to see if we can generalize to the case of these hypergraph models, because the free group is like the base space, it's the one of fixed dimension. And then if we have a group where the coordination number effectively isn't uniform, the neighborhood structure of the vertex count isn't uniform, then you can think of that as being a surjection from the free group onto the Cayley graph of that group. And then you can define things in terms of then you can define local changes of dimension in terms of local changes in kind of neighborhood structure. So anyway, that was probably a little bit incomprehensible, and it's in part incomprehensible because I don't fully understand it yet. But I just wanted to give a kind of a conjectural idea for how local dimension change might be formalizable, even though the mathematics for this doesn't yet exist. We're having to invent it more or less in real time. And so and in fact we could go a little. The reason I put these pictures in is to illustrate that we could go a little bit more general than this, because we're not. Because our notions of dimension and curvature don't depend on individual GD6 individual adjacencies. They actually depend on kind of on average adjacency structure. They depend on finite length GD6 rather than just single hyperedges. You can get away actually with having a graph that's not vertex transitive, but actually is quasi-vertex transitive, which means that effectively the number of that you don't have the same, that not all vertices have the same neighborhood structure, but you have a finite number of different neighborhood structures, into which every vertex in the graph can be put into one of those different families of neighborhood structures. So these are examples of quasi. There's like tetrahedral graphs, dodecahedral graphs, buckyball graphs. These are all examples of kind of quasi-vertex transitive graphs that would also be good candidates for a possible fixed dimensional base space within which, or with respect to which, to quantify global dimension change. Okay, so here are some examples. That was all a bit abstract. Let me give some specific examples. So these are Cayley graphs for the free group on 2 generators. Obviously, these are infinite things in general, because although it's a finitely presented group, it's a finitely presented group with an infinite Cayley graph. So this you can think of as being like a beta lattice. And then these are examples of Cayley graphs for symmetric groups. So effectively what we're doing, so the only difference between these and those is that because these are free groups, these don't have any, they're just generators. There are no relations between the elements. These have both generators and non-trivial relations, which is why you get effective merging of vertices in the Cayley graph. So those are symmetric groups. These are examples for alternating groups. This is a way in which you can, again, purely with respect to geometric group theory, consider a combinatorial structure that has a well-defined infinite limit as some continuous thing. So this is a sequence of Cayley graphs whose limit in the infinite case is known to be the Heisenberg group, which is of course a group that you would conventionally represent in terms of continuously varying quantities, but it's nevertheless its presentation is something you can build up as an infinite limit of combinatorial presentations, which is kind of amusing. Okay, so like I said, we're hoping maybe some people at the summer school may be able to figure out in more detail than I understand exactly how we can go about developing a general theory of general relativity for varying dimensional manifolds and importing techniques of differential geometry and algebraic topology over to the case of sort of manifolds where you don't have connected components that have fixed dimension. But so we don't know the correct way to analyze that. But just because we don't have the correct way to analyze it doesn't mean we can't do computer experiments. And so that's kind of something we've done. And it turns out, there's a fairly general class of these systems that have this rather nice property that their effective global dimension changes over time. And that's amusing because we think that has a bunch of implications for early universe cosmology. So the way that basically works is if you imagine, okay, so in order to get the Einstein equations, one thing we had to do was to assume that the causal network that we get out and the hypergraphs we get out, have ultimately finite dimensions. So in other words, what that means is if you start out with a hypergraph or a causal network that's very, very densely connected, that exists in effectively infinite dimensions, then in order for it to satisfy the Einstein field equations, it has to converge down to something that's finite dimensional. So in other words, it has to go from something that's very densely connected and through the dynamical procedure that is the application of the updating events, it has to converge down to something that's sparsely connected. And so you can think about that as being like, the early universe is extremely causally connected and then becomes more sparsely causally connected as the universe evolves. And so that's immediately interesting because obviously increased causal connectivity of the early universe is kind of the main reason why people like Alan Guth and Andre Linde considered inflationary models of cosmology back in the 1980s. So, and so it turns out that actually we can reproduce basically all the kind of conformal consequences of space-time for things like inflationary models of cosmology without having to postulate inflation, without having to postulate something like an inflaton field. And the way we can do it is by this process of starting out with hypergraphs that are effectively infinite dimensional and that converge down to hypergraphs that are finite dimensional. Because if you have a hypergraph that's arbitrarily well connected, that's arbitrarily well causally connected, you can think about that as being like a universe where the effective speed of light is very, very high or even infinite, right? Because you're basically saying information can propagate through the hypergraph much faster because of the increased connectivity than it otherwise would have been able to. So we can model this in a very toy case. You could model this as being like it's a universe where the speed of light is just a scalar field, we could consider a scalar field that's kind of continuously varying, but it's actually even easier to consider a scalar field where there's just a discontinuity given by some Heaviside step function, which I'll call theta. So there's effectively some phase transition that happens in the early universe where we go from some universe where the effective speed of light is really high to a universe where the effective speed of light is comparatively low, i.e. where it has effectively its present value. So then you can ask, okay, if that happens, what would that look like? Well, we can write down, if we take the FLRW metric, that is the Friedmann-Lemaitre Robertson-Walker metric for an expanding universe, that's the sort of the most general homogeneous and isotropic space-time line element that exists in general relativity. It's the basis, it's the sort of basic metric one considers in things like lambda CDM cosmology. And so then if we introduce this phase transition in C governed by where this phase transition takes place at some point TC, then now this FLRW metric essentially factorizes into a pre-phase transition and a post-phase transition metric. So we have this bimetric form. So this is essentially the pre-phase transition metric, and this is the post-phase transition metric. So what we end up with are two separate light cones for the universe, and their size is governed by some dimensional ratio, which we'll call gamma. And then the reason why that's interesting is because now if we compute the horizon scale, we can see that the horizon scale, for, as long as the initial value of the speed of light c0 is sufficiently large compared to the final value cm, then we can determine that the proper horizon scale is much larger than it would have been if the effective speed of light had been constant. And so in particular, one obtains in the limit as gamma goes to infinity, the proper horizon becomes arbitrarily large, and so we can deduce that sort of everything, all points of space must exist in the forward light cone of the initial singularity. So in other words, everything is causally connected, and therefore, in particular, it's the region of causal connectivity is much larger than the region from which we are currently receiving photons from the cosmic microwave background. And so the fact that we see effective isotropy and homogeneity in the horizon is unsurprising if such a phase transition occurred. So it does constitute a valid solution to the horizon problem. Also excitingly, it constitutes a valid solution to the flatness problem, because if we take the standard Friedmann equation, the equation that describes an expanding universe with scale parameter a, where the Hubble parameter h is effectively governing the rate of change of that scale parameter, then as long as we assume there's no cosmological constant, we can reformulate the sort of the effective rate of the ratio of the effective speed of light to the effective change to the effective rate of expansion in terms of this parameter epsilon, which is that's the parameter that you would sort of probe when talking about the numbers of e-folds of inflation and so on that one would see in the early universe. Then in terms of that parameter, you can construct this other quantity omega, and then which is also a quantity that people sort of investigate in terms of expansion rates of the early universe. And you can just examine what is the rate of change of epsilon. And so then again, assuming a universe which is radiation dominated, assuming that the cosmological equation of state, that your P over rho quantity is of the radiative form, then what you end up with is a cosmological attractor solution where the epsilon, the number of e-folds, is approximately 0, and that corresponds to a universe that is approximately spatially flat. And so again, as long as there's an effective phase transition in the speed of light, and as long as the discrepancy between the early time speed of light and the late time speed of light is sufficiently large, you end up with a universe that's homogeneous and isotropic, and which also has approximate spatial flatness. And so you end up with something that's kind of observationally indistinguishable from a universe that was generated by inflationary cosmology without actually having to postulate inflationary cosmology, which I think is really, really neat. And again, I think, I forget who's working on this. I think it's Daria, right, is possibly going to be investigating to see whether it's possible to find examples of these hypergraph systems, in which one starts from very arbitrarily well-connected hypergraphs, which then have some phase transition in their global dimension that cause them to converge down. And then the really exciting thing would then be to see if we can define something like a heat equation on a hypergraph with exhibiting this kind of global dimension change. And then determine, and so effectively you can simulate some coarse approximation to the CMB, and then you could actually see explicitly whether you end up with a CMB that's roughly homogeneous and isotropic, whether you get sort of initial density perturbations like you'd predict in inflation, those kinds of things. So this is an area that I'm personally really excited about, this connection between global change in dimension of the hypergraph and apparent sort of exponential expansion in the early universe, and apparent variation in the value of the speed of light. Just one final note, and then we can move on to quantum mechanics, which is the thing we're actually supposed to be discussing here. But so in retrospect, thinking about it like that, it's not entirely surprising that there should be a connection between the number of dimensions of the hypergraph and the effective rate of expansion, because that's actually that's a property that you see already in ordinary general relativity, in ordinary relativistic cosmology. Because if you take the Friedmann-Lemaitre Robertson-Walker element, there's nothing to even though it's conventionally written in 4 dimensions, the definition of the Euclidean metric extends to arbitrarily many dimensions. So there's nothing to stop you from just writing it in an n-dimensional form like this in terms of the Euclidean metric delta ij. And so then what you can do is if you say, let's assume a perfect relativistic fluid where you're essentially assuming a radiation, a cosmological equation of state that obeys this conservation law, so which is like the higher dimensional analog of mass conservation or energy density conservation, as I should say. Then and you just substitute that in as the effective equation of state for your n-dimensional universe. What you end up with is a reduced form of the Einstein field equations, with this cosmological equation of state. And then the actual, and then if we take the FLRW equations and we solve this system of differential equations for the scale parameter, for the parameter A that tells you effectively the length scale of the universe, the expansion scale of the universe, you end up with something that can be computed analytically, and it has this general form. I won't ask you to prove it, but this is this is a computation that you can in principle do I mean, if you want to try sticking this into DSolve, you're welcome to do it. It will give you the right answer, but it's a little bit ugly. But anyway, so what this is telling you is that there is an exponential relationship between the effective dimension of the space and the perceived expansion rate of the universe. And of course, as I say, that at least on a phenomenological level, that's exactly what we see in these hypergraph models. And I'm really looking forward to getting kind of more actual data from these computer experiments to confirm that this is actually true. So, but at least at a theoretical level, this is very promising because it means that this general prediction that global dimension change implies effectively global variation in the effective speed of light, and that is related to to a universe which has the same conformal structure as one that's exponentially expanding. As I say, the fact that that's a generic prediction of our models, and it turns out it's something that exists in ordinary general relativity as well. That's something I think is really quite exciting. So I believe that's the end of that particular thing. We could take a couple of minutes if people want to take a break or people want to ask questions before we move on to quantum mechanics. But was there? I know that there were a bunch of things that we couldn't. Oh, sorry, that's my Spotify list. Zoom is not opening for me. If I stop sharing for a moment. I know that there are a bunch of questions that came up this morning that people might want to have answered if they're still interested, but otherwise we can just take a few minutes of break and then we can move on to the quantum mechanics stuff. John, you have unmuted yourself. Is this?
I had a quick question about this.
Sorry, something went wrong with my audio. I missed the first part of that. Can you, sorry, just repeat?
Yeah, this is John. I just had a quick question.
Hey.
This dimensionality reduction, is it something that is the discontinuous that you would expect, like a phase transition, or might it be sort of
No, I would suspect it's continuous, but I don't.
Right.
I don't have the mathematical ability to analyze it in the continuous case. The only case where I was able actually to prove anything is in the case where we considered it to be effectively discontinuous. Like I say, we're basically bitten by the fact that no one has developed a theory of differential geometry that works in varying dimensional spaces. That's something we're hoping people will do, but it's just that the math doesn't exist yet. The closest thing that
would have any bearing on whether the universe is open or closed, or is it?
That's an interesting question. So, and we don't know. I mean, this is that's a sufficiently the derivation of things like the Einstein equations and inflationary cosmology are sufficiently generic that we don't, that they're compatible with de Sitter universes, anti-de Sitter universes, flat universes. We don't yet have enough kind of external data to know what the eschatology is, so to speak. What the final geometry will look like. And I believe there's a project. Oh gosh, I forget who we assigned it to now. If the person we assigned it to is in the room, please speak up. We assigned a project yesterday that was about looking at pairs of hypergraph rules where one grows the universe, one contracts the universe, and seeing whether you end up with, seeing what the final stage is. Who ended up with that project? I will remember in a minute.
I think it was Sam.
Was it Sam? Is Sam in the meeting? No, he's not. Maybe not. Okay, that was. There is a project this year. There is at least one project, probably multiple in the end, that will be investigating that. So that, yeah, but that's a good question. We don't yet know. I should say, by the way, on the varying dimension thing, the closest sort of field that I've been able to find that the field that I found that has come closest to addressing that question is this thing called scale relativity, which are a bunch of people who tried to, it seemed to be popular a few years ago, and no one seems to have published anything on it since, but where they were trying to effectively generalize general relativity to the case where you have manifolds where, in addition to Lorentz invariance, you also have effectively scale invariance. And one of the interesting things about that is if you have scale invariance, then that gives you a way of kind of defining Einstein equations over fractal manifolds, whatever a fractal manifold is. So that seems like something would be potentially very relevant. But as far as I can tell, in the literature I've seen, the scale relativity people haven't actually succeeded in that goal. They tried and it doesn't seem to have gone anywhere. But maybe I'm wrong. Maybe I just missed something, but I couldn't find anything. Did anyone else want to ask anything? Or
Just have a very basic question about the variable speed of light. So fascinating idea. It definitely goes against sort of historic precedent for the constancy of the speed of light. I'm just wondering if you can give me a snapshot of, since you're in a position I'm not in to see sort of across the field, how well is this received right now, or is this still going to be a bone of contention, so to speak?
so with respect to the variable speed of light in particular? Yeah. Okay. This is a really good question. So, and the thing to say about that is actually this is not the first model that has implied the variable speed of light. That in fact, there's the whole field of VSL cosmology, variable speed of light cosmology, that has investigated this. And so there are people like Pettit and Olbrecht and Moffat and a bunch of others who've developed models of variable speed of light cosmology. And so, so this idea that you could use a variable speed of light as a way of solving the horizon and flatness problems, that's not a new idea for this project. What this project what this model gives you is actually a dynamics that explains why the speed of light is varying, right? It's saying that because the hypergraph is starting off as very high dimensional and converging down to something low dimensional, one naturally ends up with a universe where the maximum rate of information propagation reduces, and so it kind of explains why a VSL cosmology might be true. So that's the first thing I would want to say about that. But then, so you ask, how has this been received? VSL cosmologies, I think, they're treated as being fringe but respectable. Would be my basic assessment. I'm not an expert in that particular area. I think VSL cosmologies are cool. I don't think anyone thinks that they're cranks. But it's also not, it's not as mainstream as inflation. But then inflation is not a particularly well-developed theory, in my opinion, either. So I think there's no reason to believe it's obviously wrong. It implies some funky stuff. So if you have a speed of light that's allowed to vary not just in the early universe but over the whole universe, then that implies various things about variation in the fine structure constant, and then that does lead you into some issues about that. I think there are various astrophysical experiments that have been done about looking at the fine structure of silicon and things that have been observed in spectra from supernovae and things that sort of put bounds on the degree to which the fine structure constant could have varied in the course of our universe. I don't know very much about those experiments other than the fact that they indicate that the fine structure constant probably hasn't changed. And so that means that if there is a variable speed of light, A, it doesn't change the fine structure constant, which would be a bit weird, or B, if it does change the fine structure constant, then it must have happened, all the measurable variation in the speed of light must have happened really, really early, before things like stars and so on with spectra that we can observe actually had time to form. Yeah, it's a super interesting question. I'm not an observational cosmologist, so I don't know. I don't really know the answer, but that's something we'd be really keen to figure out.
No, that's terrific. Thanks a lot. That's great.
Yeah, no, my pleasure.
Jonathan, I had a question if there's still time.
Yeah, absolutely. I want to take a break for a few minutes. Yeah, go on.
So if this kind of phase transition or transition between dimensions is happening when there's already a continuous geometric interpretation of the graph, my assumption is that if you really looked at a continuous model where you had all the consistency, what you would end up with is basically an effective inflaton field describing this. And your output would be, you would get all the parameters of the effective Lagrange inflaton field for any of your given update rule, which would be great. I mean, that I think is a sense in which inflation is not well developed as in a real good reason to expect any particular inflationary model. But I'm wondering if that is the setup you have in mind, or if you have in mind the situation where you don't have you are resolving these problems before you have your continuous limit.
That's a really, really awesome question. And so I have neither scenario in mind, in the sense that I obviously we don't know. It's a really good question of whether this, if there were a rapid phase transition in the effective dimension of the universe, whether it occurred at a time scale where discreteness was still important. That's a super interesting question. That's one of the reasons actually why we put in, I think one of the projects on the list was about looking at the kind of the network structure of the cosmic web. It's a slightly crazy idea for a project, but one of the reasons why we thought that would be interesting to investigate is that if the phase transition occurred at a time scale where you didn't have a continuous geometry and where discreteness was still relevant, one might expect to see the actual network structure of the hypergraph essentially imprinted on the large scale structure of the universe, potentially in something like the cosmic web. Like I say, it sounds a bit nuts. I'm not entirely sure if it's actually true, but I thought it's something that might be interesting to investigate. But yeah, so to answer your question, we don't know. I agree with you that it seems overwhelmingly likely that what you would end up with, if you do have a continuous geometry, is something like an inflaton, something like a slow roll inflaton potential. I completely agree. That probably is the most plausible scenario. And I also agree that the sense in which I think inflationary theory is not well developed is, the relativistic side, the cosmological side is perfectly well developed, but the actual detailed particle physics of why is there an inflaton and how does it couple to other quantum fields and things. Again, not being a particle physicist, I can't speak too authoritatively about that, but my understanding is that's still very much an open question. And potentially if global dimension change at a continuous scale does produce an effective inflaton, it has a way of answering it, which I think is kind of cool.
Thanks.
I hope that makes sense. Did I say anything obviously false?
Oh, that was great. Yeah, that was resolved. Thank you.
Okay, cool. All right. Okay. Well, I guess if no one else wanted to ask anything immediately, obviously we have a discussion session and things after this, and I'm going to try and end this early so we can all take a break for half an hour or longer before that all starts. But since we have everyone here, let's make a start on talking a little bit about quantum mechanics. Okay, so here's the big picture. So far, everything we've been discussing has ignored multi-way systems. We started by saying, the evolution of one of these Wolfram model systems is non-deterministic because there are generally many different updating orders. There are generally many different places where rules can get applied, and different updating orders will yield different non-isomorphic spatial hypergraphs, and hence different evolution histories for the universe. But then we said we're going to impose this condition, which is causal invariance, which is kind of our excuse for not having to think about multi-way systems, because it's what guarantees that even independent of which updating order you choose, the causal network you get out is always the same up to isomorphism. But now what I want to do in order to address the question of how can this model relate to quantum mechanics is go back to that initial assumption. What if instead of having to get rid of multi-way systems, what if we say that multi-way systems are actually really fundamental? So this is everyone's favorite multi-way system that we started with, I think, in the first lecture. And then we said, let's assume that all the branch pairs converge, that one has effective global confluence, and moreover that one has causal invariance, and we'll use that to derive special relativity and general relativity. But one thing that I'm sure that will have occurred to many of you is that these multi-way systems, these multi-way evolution graphs, are very path integral-like, right? In an ordinary path integral, you say that the trajectory of a quantum system is described by a sum over all possible trajectories, a functional integral over all possible trajectories, where each trajectory is weighted by a quantum amplitude, or more precisely by this phase term e to the is sx dot, which is the action in terms of the Lagrangian density. And so this gives you a way, given the overall wave function, it gives you, given the initial value of the wave function, it gives you a way of computing the overall wave function for any future time. And so this notion of taking functional integrals over all possible trajectories is very much like it does seem very much like the continuum analog of a multi-way evolution graph. And so again, just as the actual path integral is not, we don't really know how to make the path integral mathematically rigorous in ordinary quantum field theory, because we don't know how to define integration measures over over infinite dimensional function spaces. In much the same way, we don't know how to make this correspondence with the path integral fully mathematically rigorous, but I want to kind of give you some indications of how that correspondence might work and why we think it actually is true. And I'm going to present some heuristic mathematical evidence for why that might actually be the case, and what the translation between the path integral formulation of quantum mechanics and the multi-way system formulation of Wolfram model evolution might actually be. So the basic idea is, if we have a multi-way system, there is a natural measure that gets defined on it. There is a natural, and that measure is essentially in terms of path weights. So given a particular state in the multi-way evolution graph, we can ask how many incoming paths to that state yield that particular state. How many distinct ways were there of achieving that particular state? That gives us a natural way of weighting the vertices in the multi-way evolution graph, and hence gives us a measure over which we can integrate if we take a sensible continuum limit of the multi-way system. And so the conjecture that I kind of want to suggestively place in your minds is that is like the dx integration measure that appears in the standard sort of quantum field theoretic formulation of the path integral. Okay. So now let me build up some terminology from mathematical logic that's going to help us to make the correspondence between multi-way systems and ordinary and things you would think about in ordinary quantum mechanics. So the first is this notion of a critical pair. So a critical pair, loosely speaking, is, if you have an abstract term rewriting system, if you have a system where you have an abstract rewriting system where every element is a term, every element is an expression that contains nested sub-expressions, like in the case of a hypergraph, then you can define this notion of a critical pair, which is like the minimal notion of an ambiguity in terms of the application of the term rewrite. So it's saying that effectively your two rewrite operations can overlap with each other, that there's a common sub-expression to both that is unifiable with either the same rule or the same rule being applied in two different places, or with different rules in some finite rewrite system. And so when that happens, you get this thing called a critical pair. So a critical pair is the statement of the ambiguity. So in the context of our multi-way systems, a critical pair corresponds to an elementary bifurcation in the multi-way system. It's an indication that either there was the same updating event that could get applied in two different places, or there were two different updating events that could get applied, and that they yielded different non-isomorphic states. So non-isomorphic spatial hypergraphs in the actual hypergraph case, or non-equivalent strings in the case of in this sort of string toy model. So, for instance, if you have a particular term rewriting system that maps, f of g of x, y, comma z onto g of x, z, and g of x, y goes to x, then this system has one non-trivial critical pair associated with it, because both of these elements can be derived from a common sub-expression f of gx, comma z, by applying a single rewrite step. You can also consider the case of trivial critical pairs, where there are two different rules that could get applied, or the same rule could get applied in two different ways, but they yield the same common expression. So in the multi-way system, that would be a pair of evolution edges, but where they both yielded the same state. And so in the multi-way system, we happen, in the standard way we set these up, states corresponding to trivial critical pairs get automatically merged, and states corresponding to non-trivial critical pairs are kept as separate. But there's as I'll explain in the talk I'm going to give on Thursday, I'll show you actually how to use the multi-way system code, and in particular by including state IDs, or by requesting the unmerged evolution graph, you can consider not just the non-trivial critical pairs, but also the trivial ones as well. Okay, so then if there is a critical pair, if there is an elementary bifurcation in one of these multi-way systems, you can then ask the question of, does that critical pair converge? Does it reconverge on, do the two elements of that bifurcation eventually reconverge on some common state? Now, of course, that's exactly the same question that we considered back when we were thinking about special relativity as a means of defining global confluence, which, as I mentioned, is intimately related to the causal invariance property. So effectively, you can think of a strengthened version of global confluence is exactly the statement that every critical pair sorry, no, not a strengthened version, a weakened version of global confluence, which is local confluence, is exactly the statement that every non-trivial critical pair is forced to converge. So in other words, we can say that if we have a critical pair x, y in some rewrite system, then it's convergent if there's some common element z, such that there's a finite rewrite sequence mapping x to z, and a finite rewrite sequence mapping y to z. Now I mentioned that this local confluence property, this property that critical pairs are convergent, is a weaker version of ordinary global confluence. But there exist cases in which it's actually equivalent to global confluence, and those cases are exactly the cases where the rewrite system terminates, where instead of the multi-way evolution graph kind of extending off infinitely, everything just converges down to some common state. And so, that would correspond to a rewrite system that we would describe as strongly normalizing. And so in the case of a strongly normalizing rewrite system, it turns out that weak confluence and global confluence are exactly the same. I'll discuss it in slightly more formal detail what that means and how we derive that in just a minute. But so the basic idea is if we want to know local confluence, it's really easy. We just compute all the critical pairs, all of the elementary branchings in the multi-way system, and we see whether they converge. Now, I say it's easy. It's conceptually easy. Algorithmically, it's really difficult because actually this is an undecidable problem because it's equivalent to solving the word problem for finitely presented groups, and we know that problem is undecidable. This gives us immediately gives us a sort of a fairly quick way of determining possible causal non-invariant rules, because if we can find a critical pair and we can show that it doesn't converge, then we know that the system is not locally confluent, which means that it's not globally confluent, and therefore by extension we know that it can't be causal invariant. And so in the same way as, you can think of disconnected regions in the causal network as being separated by something like an event horizon. The suggestive conjecture that I'm going to make to you now, and hopefully be able to back up a little bit later on, is that if you consider multi-way branches that are disconnected, those can be thought of as being like superselection sectors in some projective Hilbert space. So obviously in ordinary quantum mechanics, once you're in a particular superselection sector, it's effectively like you can't get out. That's kind of our conjecture is that's the multi-way analog of causal disconnection due to the presence of an event horizon. Okay, so let me describe in a bit more detail what I meant by this distinction between local and global confluence and this notion of strong normalization. So we can say that an object is reduced to some normal form if it's no longer possible to rewrite it any further, if there doesn't exist some element that is the successor element of that state. So if it were the case that we reached some point in the multi-way system where there was just some state and we couldn't go any further, there was no more rewrite we could apply to it, we would say that that element was a normal form, that state was a normal form. So then we can describe a multi-way system or an abstract rewrite system as being weakly normalizing if every finite rewrite sequence, let me say that again. We can describe it as being weakly normalizing if there exists some finite rewrite sequence, and we can describe it as strongly normalizing if every finite rewrite sequence terminates at some normal form. So a weakly normalizing multi-way system would be one in which every branch of the multi-way system, independent of which state you get to, there is some branch of the multi-way system which allows you to reach a normal form. On the other hand, strong normalization, which says that every finite rewrite sequence terminates at a normal form, would correspond to the statement that it's not that you can find a branch that terminates, it's that every branch is guaranteed to terminate. And like I say, the reason why that's kind of important is because if the system is weakly normalizing, there's this result called Newman's lemma, or if it's weakly confluent and strongly normalizing, then there's this result called Newman's lemma, or the diamond lemma, that says that global confluence is equivalent to local confluence in that particular case. So in other words, as long as we have a multi-way system that eventually terminates at some common state, then we know that branch pair convergence, critical pair convergence, is both a necessary and sufficient condition for guaranteeing causal invariance. So actually doing causal invariance testing for multi-way systems where every branch eventually terminates at some normal form state, that's for those systems, algorithmically determining causal invariance is really, really easy. But of course, the systems we're actually interested in are the ones where the multi-way system doesn't terminate and where everything goes on ad infinitum. And then Newman's lemma no longer applies, and there's no longer any decidable finite process for determining causal invariance. One of the things we want to investigate, but we haven't investigated yet, and as far as we know, no one in theoretical computer science has investigated it yet, is the question of whether there is some sort of probabilistic analog of Newman's lemma that also applies for rewrite systems that are not strongly normalizing. So that if you know that some fraction of critical pairs necessarily converge, does that give you some bound on how likely the system is to be globally confluent or even locally confluent? We don't even. As far as I know, there isn't even a sensible way of formulating that question yet, but it's one that we'd really like to know the answer to. Okay, so So although critical pairs is the terminology that gets used in mathematical logic, because these things are associated with branchings in the multi-way evolution graph, we think critical pairs is actually a little bit too obscure as a piece of terminology. So we've started calling them branch pairs, and we're trying to make this terminology catch on somehow in the world of abstract rewrite systems. So if we consider the evolution of this system, which I think corresponds to wait, no, I don't have a picture of it. Maybe I have a picture of it later on. But if we consider a hypergraph system like this one here, we can therefore compute what are its branch pairs, what are the elementary bifurcations that exist in the multi-way system, what are the ambiguities in the elementary ambiguities in the updating order. So in this case, there are 14 kind of main branch pairs that appear when you first evolve the system. But it turns out after those 14 branch pairs have appeared, if you go another time step, 6 of them resolve. 6 of them resolve within a single step, these particular 6. If we go another time step, 8 of them resolve. And so we can determine that this was a system, assuming that this was a terminating rewrite system, assuming that it was strongly normalizing, this would guarantee that this has to be a causal invariant system, because every branch pair converged within 2 update steps. So it's not as causal invariant as a system where everything converged within a single rewrite step. But it's still nevertheless causal invariant. It's still locally confluent and hence globally confluent, and therefore, and moreover, because it's strongly normalizing, it's therefore also causal invariant. This is a more complicated example of that that illustrates why causal invariance testing is so difficult to do. So if we consider, so this slightly modified hypergraph rewrite system, this time it produces 58 branch pairs after a certain amount of evolution. If we go a single time step onwards, then 6 of them happen to resolve. But if we go a further time step, none of them resolve. None of the remaining ones resolve. If we go another time step, again, none of them resolve. And so, of course, in principle, we'd have to go to infinitely many time steps in order to know for certain that these were not going to resolve. But we can start to build up kind of heuristic evidence that, in fact, the system is probably not causal invariant. But this is, as I say, this is an undecidable problem. We can't know in general. Okay, so the point that let me try and motivate my reason for introducing all of this. We've already established that causal invariance is what we need in order to get special relativity and general relativity in the continuum limit. But we've also established that kind of having non-causal invariance, having bifurcations in the multi-way system that don't necessarily immediately reconverge, appears to be necessary for getting at least some aspects of quantum mechanics. And so for a long time, that was a major concern of how you can make the necessary causal invariance of special relativity and general relativity compatible with the apparently necessary non-causal invariance of quantum mechanics. So then about a year ago, I made a conjecture that it has to do with this concept called Knuth-Bendix completion, which is a pretty abstract idea that comes from automated theorem proving. But basically what it allows you to do is to start from a rewrite system that is not globally confluent, that doesn't satisfy causal invariance. And by applying effective update rules that cause critical pairs to converge, that force convergences between branch pairs, it allows you to end up with a rewrite system that is still, after a certain number of applications, that still appears to be globally confluent. So I'm going to just quickly run you through roughly how that works. Although, understanding the algorithmic intricacies of the Knuth-Bendix procedure is probably not required in order for you to understand how quantum mechanics works in these models. But the basic idea is we're given a strongly normalizing rewrite system that is not globally confluent. What we want to do is to construct a new rewrite system that is globally confluent, but which preserves kind of the large-scale structure of the original rewrite system, where in this case, large-scale structure refers to what's called deductive closure. So the deductive closure, if the rewrite relations are symmetric, so everything is just an equivalence relation, the deductive closure is essentially it's the set of equalities that you could prove using with some finite proof method, given the original set of equivalences. So what you're trying to find is a rewrite system that preserves the deductive closure, but which introduces global confluence. And so, as I say, you're considering symmetric rewrite relations where x goes to y goes to x for all x and y. And so what Knuth-Bendix completion does is it computes the critical pairs of this rewrite system, and then it imposes new equivalences between those objects that force those pairs to converge. And then once you've converged enough of them, once you've forced enough of these elementary branch pairs to converge, you've guaranteed that you have global confluence. And so then one thing that we had to do in order to make this work in our case is generalize it for the case of potentially asymmetric rewrite relations, because of course our hypergraph rules are not necessarily symmetrical in time. So so to do that, actually, it turns out it's not particularly difficult. You just consider the binary relation that is the rewrite closure of the abstract rewrite system. So it's the smallest rewrite relation that contains the set of rewrite rules. And then you can construct its converse closure, which is effectively the closure of its that's the closure of its converse relation, and that gives you a way of sort of simulating a symmetric rewrite system from within an asymmetric one. And then you can ask about the deductive closure with respect to the converse closure of that rewrite system. And so then if you imagine, okay, in the symmetrical case, let me just quickly walk you through an example. If you consider this symmetrical case, then these are rewrite relations that happen to correspond to axioms of standard group theory, the axiom of identity, of left identity, left inverse, and associativity, respectively. Then it's possible to prove group theoretically that this theorem holds, that these two terms are equivalent with respect to the reflexive transitive closure of this equivalence relation. And the way you can do that is by determining that there exists a finite deduction chain that leads from the left-hand side to the right-hand side. And so that implies that this equivalence is an element of the deductive closure of E, even though it isn't an element of E itself. And we can do exactly, and again, using this generalized method, we can do exactly the same argument and apply it to the case of the asymmetric rewrite relations as well. So if instead of having bidirectional rules for the group theory, if we just had single directional rewrite rules for group theory, then this, although this theorem would be an element of the deductive closure because there exists a unidirectional rewrite chain that allows you to join the left-hand side to the right-hand side. On the other hand, this original theorem that we proved in the symmetrical case wouldn't hold because now, because these rules are unidirectional, there isn't a way to apply a right-to-left variant of the associativity rule, which is what you would need to do in order to reduce the left and right-hand sides onto some common normal form. Okay, like I said, that was all a little bit abstract. So that's giving you at least a little bit of background about what this Knuth-Bendix completion procedure is and why it's used in mathematical logic. But how can we use it in one of our multi-way systems? So here's a really simple example of that. So here is an example of a system that terminates at some normal form. It's weakly normalizing because there are normal forms for any state. There is a branch you can reach for which that branch terminates at some normal form. So you can see here's an elementary example. Because there's no rule in the system that has B on the left hand side. Once we obtain a B here, there's no more update that can get applied here. So this is an example of a normalization point, a point where we've achieved a normal form in the multi-way system. And therefore, because we've achieved a normal form on one branch, we know that the system can't be causal invariant because this is an elementary branch pair, an elementary critical pair, which definitely doesn't reconverge. And so the question is this is something which is non-causal invariant, which is a fundamentally kind of quantum mechanical multi-way system. So then the question is, how can we make this compatible with special relativity and general relativity, which require causal invariance? So essentially, the big picture sort of philosophical idea that I had was maybe the reason why quantum gravity is hard is precisely because quantum mechanics requires confluence and quantum mechanics requires non-confluence and relativity requires confluence. And so you have to have some way of bridging the gap between the two. And so it turns out Knuth-Bendix completion gives you a way to do that. And so my conjecture was that this would be related to the process of quantum measurement. And that's now become kind of our interpretation for how the measurement process works within the context of these Wolfram model systems. So I'd now like to kind of quickly walk you through how that goes. So if we add a completion rule that allows you to link B to AA, then that gives you a way of just immediately resolving this branch pair. So if we do that, what we end up with is this thing here, where now you can see all of these elementary branch pairs that were not reconverging because they terminated at normal forms. Now they're able to converge because now there's a way to get from this state to that state that didn't exist before. We haven't changed the rewrite closure. We haven't changed the deductive closure of the system. It's still, the same set of rewrite relations that exist between elements also exist in the completed version. It's just that now it's possible to prove global confluence where we couldn't prove it before. So my kind of hypothesis was that maybe this is what an observer is doing, that the observer is some extended object in the multi-way system, some extended object in the multi-way evolution graph. They're seeing the underlying system, the rewrite system for the universe is non-causal invariant, it's non-confluent, and therefore quantum mechanical. And what the observer is doing is they are imposing a completion procedure that allows them to perceive the universe as being relativistically invariant, even though the actual microstructure of the universe might not be. And okay, I'd like to make that correspondence a bit more precise. So one thing that's, sorry, before I do that, one thing that's worth mentioning is, so this was a case where just there was a really simple completion procedure that we could apply that allowed all of the branch pairs to converge within a single step. But that's not generically going to be the case. That generically it could require arbitrarily many steps before one achieves causal invariance, even post-completion. So if we have a string substitution system like this is one that is definitely non-confluent. It has a bunch of places where there are critical pairs that definitely don't reconverge. I mean, here's an example of one because BB is clearly a normal form. But if we look at the relative rates of branch pair resolution and non-resolution, we can see that even after adding a sort of minimal set of completion rules that guarantees causal invariance, the branch pair completion time can be arbitrarily long. So even in this relatively simple case, we apply this particular pair of completion rules, which we can prove are the minimal set that's needed to guarantee global confluence. But even after applying these completion procedures, it can take an arbitrarily large number of multi-way evolution steps before things sort of converge down to a common state. So even post-completion, this is still a computationally expensive process. Okay, so like I say, how do we make a correspondence between this and ordinary quantum mechanics? So the idea is that in the same way as an observer in relativity is defining space-like hypersurfaces, is defining a foliation of the causal network into space-like hypersurfaces, into sets of events that they can consider to be simultaneous. The basic principle here is that in quantum mechanics, what the observer is doing is they're observing the multi-way evolution graph. And so what they're doing is they're foliating the multi-way evolution graph into a sequence of what we can call branch-like hypersurfaces, which are collections of states that the observer is considering to be simultaneous, but they're not events that are simultaneous in the causal network. Rather, they are like microstates of the universe that the observer is kind of observing simultaneously. So this is an example, again, for the toy case of a string substitution system. This is an example of kind of a default foliation for a multi-way evolution graph. So then the observer is seeing a particular sequence of what we can call branchial graphs, which are our combinatorial way of representing these branch-like hypersurfaces. So these are the particular sets of states that the observer is seeing for each step in the evolution history of the system. So that, they start off by seeing this pair of states, then this triple of states, then this set of 5 states, and so on. And then these pink edges, which are the branchial connections, those are determined by the ancestry distance, by the ancestry structure of the multi-way evolution graph. So we're connecting in a particular branchial graph. We connect a pair of states we connect them directly if they have an immediate common ancestor in the multi-way evolution graph. If they have a common ancestor that goes back, to an ancestry distance of 2, then then in the branchial graph they're going to be a graph distance of 2 away from each other. And again, skipping ahead a little bit, the basic idea is that these branchial graphs can be considered to be maps of entanglements between elementary microstates of the universe. So the idea is that because rather than the observer seeing a single state of the universe at any one point in time, because the observer is defining this branch-like hypersurface where there are actually multiple states of the universe, what they're seeing can effectively be thought of as like a linear superposition of eigenstates. So each element, each node in the multi-way evolution graph is like an eigenstate of the universe. And then when the observer defines this foliation, they define that hypersurface, they're defining which collection of eigenstates they're treating as being in superposition. And then, as I just said at the beginning, this natural measure that we define on the multi-way evolution graph in terms of path weights, purely in terms of path counting, then gives you a way of defining a magnitude for the amplitude with which is the sort of the elementary weighting of those elements in the superposition. And so again, the conjecture that I'm going to try and prove, well, I'm going to prove a special case of, and I'm going to sort of try to motivate the conjecture in the more general case, but we don't have a proof in the more general case, is that the overall multi-way evolution graph limits to a projective Hilbert space in much the same way as the causal network limits to a sort of large-scale Lorentzian manifold, and where the natural metric on the multi-way evolution graph is the standard Fubini-Studi metric tensor for projective Hilbert space. But as I say, I'll talk about that a bit more in a little bit. Okay, so as I say, in ordinary quantum mechanics, we have this notion that that each quantum state is a linear superposition of basis eigenstates, and so that idea is that when translated into this formalism, is that each hypersurface in the branchial graph is some linear superposition of the individual eigenstates that appear on that in that branch-like hypersurface. And so then the evolution of this time-ordered sequence of branch-like hypersurfaces is therefore like the evolution of a wave function, of a normalized wave function, where it's normalized in the sense that we can set up the elementary path weights in such a way that they always sum to 1. And so then you can look at the weighted evolution of these branchial graphs, of these branch-like hypersurfaces. So we can do something like we can take each vertex and we can just render it bigger or smaller based on the path counting weight, based on how many elementary paths, how many distinct elementary paths led into that particular vertex. That gives us a way of visualizing the evolution of that superposition in time and seeing the elementary magnitudes of those amplitudes. And so then what we're doing when we perform a measurement is we're taking this whole this whole wave function and we want to collapse it down to a single state. We want to a single eigenstate with some weighting. And so my point, the point that I'm trying to make is that's exactly what a multi-way, what a completion procedure, a Knuth-Bendix completion procedure does for these multi-way systems. We saw before that what we're really doing is we're taking some big collection of sort of branch-like separated states that correspond to these unresolved branch pairs, and by applying a multi-way completion procedure, by applying a Knuth-Bendix completion procedure, we're collapsing everything down to some normalized state that we can think of as being like the collapsed eigenstate. And so this is the sense in which the Knuth-Bendix completion procedure gives us an actualization of the measurement process. So what we're doing, as I say, we're taking this wave function, we're taking this branch-like hypersurface or this branchial graph, and we're collapsing it down to a single eigenstate. And then and then obviously because as I say, the magnitudes of the amplitudes are just the number of path weights, and because just for sort of combinatorial reasons, we have an effective conservation of those path weights. We know that if two paths led into a particular state and and that state is not a normal form, then two paths have to come out of it, or at least two paths have to come out of it. That's what effectively guarantees that the Born rule has to be satisfied. It's what guarantees that when we collapse everything, when we collapse the particular branch-like hypersurface down to a single eigenstate, that the path weight for the eigenstate that we observe is related to the path weights of the individual eigenstates that were in that original superposition by essentially the multi-way analog of the Born rule. So then and then just like in ordinary quantum mechanics, once you've reduced it down to that eigenstate, then it's like the evolution is purely classical. So that's in ordinary quantum mechanics, we say it's purely classical because now your a posteriori probabilities are given by some Kronecker delta function. And in the multi-way system, we see the same thing, because once you've collapsed everything down so that it's trivially causally invariant, then there's only a single effective evolution history. There's only a single effective thread of time in the universe. Okay, so that's the big picture idea of how you can start from a multi-way system that's non-causal invariant, and by applying a completion procedure, you can collapse it down to something that has effective causal invariance, and how that relates to something like a collapse of the wave function in ordinary quantum mechanics. But one question that I think is very important for you to ask, if I'm sure many of you have already been asking, is why would the observer cause a completion procedure to occur? Why does this measurement process actually happen in the first place? So I have two versions of this argument, one of which is kind of very fuzzy and heuristic, and the other is a bit more sort of mathematically solid. But let me give the fuzzy heuristic explanation first, and then maybe tomorrow, depending on, I don't know how long people want me to go on speaking for here, but maybe tomorrow we can go over the kind of the more mathematically detailed version of this argument. But the basic idea is the observer has two fundamental properties in these systems. They are big and they are not confused. Okay, so they're big in the sense that they are extended objects in the multi-way evolution graph, and they are extended objects in the spatial hypergraph. You know, observers are very big compared with the underlying combinatorial structure of the universe. And so one implication that it has is that just like in statistical mechanics, when you say that, you know, where you know, if two particles are within some distance delta of each other in phase space, if their positions and momenta are within some distance delta, then we say that they are observationally equivalent. And that's important for essentially reducing the number of microstates in thermodynamics down from the infinite set that we start with to the uncountable set that we start with, sorry, to the countable set that you need to sort of plug into Boltzmann's entropy formula. The idea is that a similar kind of coarse graining procedure is occurring in the observer. That when you look at an individual multi-way system, each of these bifurcations, each of these elementary critical pairs, that's a very, very small deviation in multi-way space. And it's a sufficiently small deviation relative to the macroscopic observer that it's a reasonable approximation to say that the observer can't tell the difference. That these microstates, which only differ at the level of a single updating event, those updating events are so microscopic that the macroscopic observer cannot possibly distinguish between those microstates. So to the macroscopic observer, the microstates appear to be equivalent. And so what we can think of, one physical way you can think about this completion procedure is that it's a coarse graining procedure that the observer is performing. So what the observer is saying is they're observing that, you know, the evolution of this multi-way system with respect to some universal time function. But then they're saying, you know, because I'm a really big observer relative to the underlying hypergraph scale, I can't tell the difference between all these different elements of the branch pairs. To me, they all look the same. And so the observer is therefore imposing an equivalence relation between the elements on the branch-like hypersurface, which is another way of saying that they're imposing a completion procedure, because they're saying that they are imposing an effective rule that says AAA goes to AABB and AABB goes to AAA, because those two states are equivalent with respect to that observer's own reference frame. And so the observer is imposing this equivalence relation between all of the elements on that branch-like hypersurface. And so then if you actualize that in the context of one of these multi-way systems, that's exactly what a completion procedure is. And so this explains why, if you have an observer that's sufficiently macroscopic with respect to the underlying hypergraph system, such that they can't distinguish between elementary branch-like separations, because of the nature of the Knuth-Bendix completion procedure, this is what guarantees that those macroscopic observers can still see large-scale causal invariance, can still see a definite single evolution history for the universe, even if the underlying microscopic rewrite rules for the universe are not themselves causally invariant. Okay, so just before I should stop talking pretty soon, because I know everyone wants a break, not least of all me. But just to give some indication of, you know, again, some elementary correspondence between the formalism we've developed for doing these completion procedures that comes from mathematical logic and standard formalism of quantum mechanics. Rather excitingly, not only do we get immediate actualizations of concepts like superpositions, wave functions, collapsing to eigenstates, measurement processes, and so on. Not only do we have ways of formulating that purely in terms of rewrite theory, we also actually have a way of formulating things like the uncertainty principle and the canonical commutation relations. And so, the basic way that works is there's an elementary notion of commutation that exists even in abstract rewrite theory. So you can say if you have a pair of rewrite systems that have the same common object set A, but have different rewrite relations, arrow 1 and arrow 2, the collection is some indexed union of subrelations. Then we can say that those two rewrite systems are commutative. They commute with each other if for any element for any element x, such that x can be rewritten to y and x can be rewritten to z using the rewrite relations of R1 and R2 respectively, then there exists a common element w such that y can be rewritten to w and z can be rewritten to w using the rewrite relations of R2 and R1 respectively. So in other words, it's exactly what you'd think commutation in a rewrite system corresponds to. If you apply this rewrite rule, if we apply rule 1 then rule 2, then we get to the same result as if we applied rule 2 then rule 1. So that's the notion of of single-step commutation, and then we can also define a notion of multi-step commutation. So if we define an arbitrary rewrite sequence from one rewrite system, and we apply an arbitrary rewrite sequence from another rewrite system, if we then swap those around and we apply a rewrite sequence from the second and a rewrite sequence from the first, then we should get back to the same result. So this is so commutation is one case in which you get kind of guaranteed convergence of branch pairs of critical pairs. And so, in other words, we know that an abstract rewrite system is globally confluent if and only if it self-commutes, if and only if it commutes with itself. That's a pretty straightforward thing to see. A much more non-trivial thing to see, which is this thing called the commutative union theorem, proved by Hindley and Rosen, is actually that there's a weak converse of that. That in fact, if you have commutativity in a family of ARSs, then there's a way of constructing a union of them such that you have guaranteed confluence in that union. And so that gives us a way of making a concrete connection between commutativity of updating events in these multi-way systems and causal invariance that as a consequence of global confluence. And so then a related result is a sufficient condition for commutativity of R1 and R2 is this sort of slightly strengthened version of the confluence property. And this is essentially the analog of the statement that strong confluence is a sufficient condition for global confluence, but this time it's saying that this sort of strong commutativity property is a sufficient condition for ordinary commutativity. Okay, so look, actually, let me show. I mean, if we just quickly run through a picture of that to make it again a little bit less abstract, so if we're saying we can apply this rule, then this rule, we can apply rule 1, then rule 2, we get to this point. If we can also apply rule 2, then rule 1 and get to the same point, then that's an elementary commutation. That's a statement that those two rules happen to commute. And every time you get an elementary commutation like that, that corresponds to a branch pair, a critical pair that converges within a single step. And so conversely, if we have a non-causal invariant system, if we have critical pairs that don't converge, then they correspond to collections of updating events that don't commute, where applying R1 then R2 and R2 then R1 get you to different points in the multi-way evolution graph, and where in effect, every pair of points in a branchial graph every pair of distinct points in a branchial graph can therefore be thought of as being a pair of points that got produced by some non-commuting sequence of rewrite events that occurred in the multi-way evolution graph. Why is that important? Well, because that's essentially the statement of the uncertainty principle, but in the context of the multi-way evolution graph. So if we think of the rewrite relations as being the linear operators that are acting on these eigenstates, as being the linear operators acting on the microstates that are the elementary nodes in the multi-way evolution graph, then you can, okay, I'm going to gloss over a slight subtlety here, which is making the distinction between updating events corresponding to sort of unitary evolution and updating events corresponding to kind of to Hermitian measurement. But then the idea is, if you have a rewrite relation that corresponds to an observation event, that corresponds to an event that measures some observable quantity A, then obviously in ordinary quantum mechanics, in ordinary quantum mechanics, you can then, if you have a pair of measurement operators that yield measurements of two observable quantities A and B, and we call those operators A hat and B hat, we can then define their commutator. So what we're doing by considering commutations of abstract term rewriting systems is doing the analogous thing, but for the case of these multi-way evolution graphs. So we're saying we can define some additional operator that is the commutator of these two elementary rewrite relations in our system. And then we're effectively asking, does A hat B hat minus B hat A hat equal 0? In other words, if you apply A hat then B hat, and then apply B hat then A hat, do you get back to the same state in the multi-way evolution graph, or do you get back to two different states? So that's so the question of whether you get effective commutation between these rewrite relations is exactly the question of whether that elementary branch pair, whether that critical pair actually converged. So then, okay, this is just standard quantum mechanics that you all know perfectly well. You can treat if A hat and B hat are themselves linear operators, then you can treat the commutator as being a linear operator. That just follows, essentially from ordinary linearity. So okay, this is probably the picture that I should have put earlier on. So this is the example of the same thing occurring in a multi-way evolution graph. So this is like applying A hat then B hat. This is like applying B hat then A hat. So this is the case where there is perfect commutation, where this branch pair actually converged. But then if you consider the case where there isn't perfect commutation, then what you end up with are two microstates that exist on the next branch-like hypersurface. Two microstates that still exist even in the next level in the branchial graph. So what we're really saying is if we consider these two updating events as being like some idealized version of a measurement operation, what we're saying in the case where they commute, we're saying that if we measure this quantity, then this quantity, if we measure quantity A, then quantity B, or if we measured quantity B, then quantity A, we'd still get the same net result. The microstate of the universe would be unchanged. If they don't commute, then it's saying that somehow the time ordering of the measurement operations actually matters, that it matters whether you measure A first or B first. So in other words, in the case where you don't get commutation between these elementary rewrite events, what we're saying is that there exists a limit on the degree to which you can prepare an experiment which measures the observables A and B simultaneously. And that's exactly what the uncertainty principle says. What the uncertainty principle says, sort of, I say, at a mathematical level, is that observations that get made of non-commuting observables necessarily take place on different branches of history with respect to some many worlds interpretation. And that's exactly what we're seeing here. When we have non-commuting in the multi-way system, what we're seeing is that those sets of events necessarily take place on different branches of the multi-way system. And so then, if and this is a big if, and it's one that I hope it's a statement that I hope to justify a bit more formally later on. If we consider the unit of distance on one of these branchial graphs, or on one of these branch-like hypersurfaces as being proportional to h bar, or in particular as being equal to I times h bar, then because, as I mentioned, anytime you get commutation, that means that you get convergence. So that means that you had two states in the branchial graph and they converge down to one state. But if you don't get commutation, that means you now have you started from one state and you end up with two states. So you end up with a critical pair. You end up with a branch pair. So in other words, you end up with a pair of states that are separated by a single edge in the branchial graph. So if the elementary separation distance for each branchial edge is IH bar, then that precisely corresponds to the statement that the commutation relation for that pair of observables is canonical, and that therefore we can think of the associated observable quantities A and B as being the Fourier transform duals of each other. So this is here's an explicit example of that. Here we can actually, this is a neat picture that Stephen produced actually of if we take a multi-way evolution graph for an elementary string system, we can actually just map out what are the individual commutation relations. We can see by just coloring them separately. Each of these diamonds that corresponds to a commutation, we can color those, and we can see where did we get a branch pair, where did it converge, and therefore we can get a kind of a visual depiction of the commutation relations for an elementary string substitution system. Hang on, what else did I want to mention? This is a bunch of complicated stuff, and I'm not sure if I want to talk about it right now. Maybe I'll leave this for a talk either tomorrow or at another time. But so one other thing that I kind of wanted to talk about just really quickly is in terms of kind of building up this dictionary between concepts in mathematical logic related to rewrite systems and multi-way systems and concepts that exist in ordinary quantum mechanics, we're starting to do that. And so one of the nice things about that is, in addition to things to elementary to rather trivial things like the commutation relations and like concepts of measurement operators and so on, we also have somewhat more non-trivial things like the concept of operator state correspondence. So in conformal field theory, there's this idea that you can biject between the set of operators and the set of states, and that idea is called the operator state correspondence, where the basic idea is for any state, you can consider constructing that state by applying some limit of an operator phi z to a vacuum state ket naught or ket 0, which is where the vacuum state is just some state that's invariant under the action of SL2z, and in the context of one of these multi-way systems, that has a very direct correspondence. That's stating that when we set up the initial conditions for one of these multi-way systems, we can effectively think of an initialization event that says, the empty set maps onto A if A is the initial condition. And so then what that means is that for any initial state, any state in the multi-way evolution graph can be thought of as being like an initial state. And so what we're saying is that any state could have been produced as an initial state by an initialization event of the form empty set goes to that state. And in fact, if you want to run the code, you can see that explicitly by running the multi-way system code and using the option include initialization events goes to true, which I'm gonna try and demo that in my talk on Thursday. And so this gives you an immediate way of interpreting the operator state correspondence in the context of one of these multi-way systems. Maybe I'll go through this quickly because this is a bunch of complicated math that's probably not not ideally suited for a talk of this structure. But I wanted to quickly, just before we finish, mention some implications that this interpretation of quantum mechanics has for things like quantum information theory. So the Knuth-Bendix completion problem, or completion algorithm, has been investigated a lot, not just in mathematical logic, but also in areas like universal algebra and computational group theory, because it basically gives you a way, if you're given a finitely presented monoid, it gives you a way of solving the word problem for that monoid. Because if you consider a monoid which has a particular generator set, then you can consider the free monoid that's generated by it, which is essentially the set of all words whose elements are taken from that original monoid. And then the elements of the original finitely presented monoid correspond to the equivalence classes of that exist in that set of words under the equivalence relation of that particular presentation. And so that's exactly a sort of an abstract rewrite system where the element set is X star, and where the set of rewrite relations is given by R by the presentation of the monoid. And so then, to solve the word problem, what we want to do is we want to find, for any individual word that appears in X star, we want to be able to find a canonical word, a representative word, to which we can reduce it in such a way that, if two words reduce to the same canonical form, then it's guaranteed to be that they're equivalent, that they are equal with respect to the original group presentation. And so that's essentially the same problem as is solved by Knuth-Bendix completion, because what we're doing is we're saying, if we think about this group presentation as producing an abstract rewrite system, what we want to do is take that and reduce it to something that's confluent, so that we can guarantee that there is convergence between these different words, and which is strongly normalizing, so that we can guarantee that there is a canonical representative word for each class of words to which we can reduce it. So here's an explicit example of that would be, if we start from the Cayley graph of the free group on two generators A and B, which I showed actually in my previous talk, and then we consider adding some relations to it. So if we add the relation that AB equals BA, now we get a non-free group which has this Cayley graph where there's actually merging between the states. So this is like merging between states in a multi-way system. And then what we're trying to do is we want to know, given a pair of words that exist in this group, are they equivalent? Are those words actually the same? And so as I say, what we want to do is we want to take this abstract rewrite system and reduce it to one where the word problem is decidable, and therefore we want to reduce it to one in which we have confluence and strong normalization. And this has also been investigated in the context of computing what are called Grosvenor bases for polynomial rings through this process called Buchberger's algorithm, which is developed by Bruno Buchberger, which is this sort of this algebraic analog of the Knuth-Bendix completion algorithm. Let me not go into too much detail about how that works. The main reason I wanted to bring this up was to point out that this completion procedure can be applied to a finitely presented monoid, because we can treat a finitely presented monoid as being like a specification of a multi-way system. Now, the reason I bring that up is because this has a bunch of interesting implications for computational complexity theory, and in particular for quantum information theory. Because if you think about what is the distinction between an ordinary Turing machine, a classical deterministic Turing machine, and something like a quantum Turing machine? Well, in an ordinary classical Turing machine, you have your initial set of states where the individual, and you have a set of symbols taken from some finite alphabet. And then you're defining a partial function, which is the transition function that tells you, given a Turing machine in a particular state with a particular tape state, what should the machine do next? What symbol should it print on the tape, and how should it evolve its internal state, and which direction should it shift the tape? So in the case of a 2-2 Turing machine, a 2-state, 2-color Turing machine, this is what you get. This is the deterministic evolution that you'd see for one of those Turing machines. If you consider a non-deterministic Turing machine, what's essentially happening is, rather than having a partial function that is your transition function, you have a partial transition relation. So in other words, for a given state of the Turing machine, it's not that you have a uniquely defined future state, but you can have a multitude of future states. So a non-deterministic Turing machine is essentially a Turing multi-way system. So that's what we're seeing here. If we look at the evolution graph for, I've misspelled the word multi-way there, but if we look at the evolution graph for all possible 2-2 Turing machine rules, we get a multi-way evolution graph. In fact, we get what's called a Rulial multi-way evolution graph that shows all possible evolution histories for those 2-2 Turing machine rules. And so that exists because, given a particular state of the Turing machine, because we now have, instead of having a partial function, we have a partial relation, there's not a uniquely defined future state. There can be many possible future states. So here's, and so then a classical Turing machine corresponds to a deterministically computed path through the space of all possible sort of Turing machine paths. So if we take a multi-way system that corresponds to a non-deterministic, to the computation of a non-deterministic Turing machine, and if we pick out a path according to some deterministic rule, what that's doing is we're carving out some particular geodesic, or I mean, actually, it may or may not be a geodesic depending on the exact details of the computation, but we're picking out a particular path through that multi-way evolution graph that happens to correspond to the evolution of a deterministic Turing machine. Okay, so then what exactly is a quantum Turing machine? Well, in a quantum Turing machine, what you're doing is, the state space is no longer a discrete space. You're replacing it with a finite dimensional Hilbert space, and you're replacing it. So your initial state is then replaced with some initial state vector. And instead of having a partial transition function or a partial transition relation, you have a partial transition monoid that has this general form. And so, in other words, what's essentially happening there is it's like what's going on in a non-deterministic Turing machine, where there isn't a uniquely defined future state for any given state of the current system. But instead of picking a future state in accordance with some non-deterministic rule, what you're doing is you're actually evolving all possible future states. You're evolving a linear superposition of all possible states of the Turing machine. So if a classical Turing machine is a single evolution path, defined as kind of scoped out by a deterministic sort of updating relation, and if a non-deterministic Turing machine is also a single rewrite path, but is kind of scoped out by the application of some non-deterministic event selection function, then what a quantum Turing machine would correspond to is the evolution of the entire multi-way system itself. It would correspond to the entire multi-way evolution graph, where we're essentially seeing a linear superposition of all possible states of the Turing machine evolving in time. So, in other words, that's what we're seeing here. So because we've replaced the transition function by some collection of unitary matrices, so some collection of automorphisms of the Hilbert space, it's no longer guaranteed to be the case that if we start from a single eigenstate, that we end up with a single eigenstate. It could be this. It could be the case that our collection of automorphisms takes a single eigenstate and converts it into a linear superposition of two eigenstates, which is effectively what we're seeing here. So we can think of this multi-way system as being like a very simple specification of the evolution of a quantum Turing machine. Okay, why is that significant? Well, it gives us a way of actualizing the measurement process in quantum information theory. Because if this interpretation of quantum mechanics is right, if it's correct that the measurement procedure in quantum mechanics can really be thought of as like a completion procedure applied to a multi-way system, then what it means is it gives us a precise way of describing the process by which you go from a state of a quantum computer to a classical sort of computational state that you can interpret post-measurement. That's something that currently in ordinary quantum information theory is highly mysterious, because of course the measurement process is a non-linear process that isn't fully understood. It can't be described, in terms of unitary evolution of the Schrödinger equation, and so what this gives us, what this mathematical structure gives us, is a way to actualize the measurement process in quantum information by saying, take the finitely presented transition monoid that corresponds to the way that the quantum Turing machine is evolving, and apply a Knuth-Bendix completion procedure to it. And what you end up finding is that the transition monoid reduces to a partial transition function, and that the Hilbert space of states that you could reach by considering the full multi-way state, by considering the full multi-way evolution, reduces to exactly to the set of states that would be achievable using a classical Turing machine. So that gives us another sort of strong piece of evidence that this this interpretation of quantum measurement is actually what's going on in real quantum mechanics, because it explains how, given the final step, and given that you've evolved your quantum Turing machine, so you now have this linear superposition of eigenstates, it explains how you were able to go from that to a classical, to a single unambiguous classical state that you can interpret as being the result of some classical computation. Because what you're doing is you're taking this branch-like hypersurface and you're applying a completion procedure to it, and you're collapsing the thing down to a single eigenstate. And again, so we can see that there's an immediate correspondence with the standard mathematical formalism of quantum information theory that allows us to reduce the finitely presented monoid of the quantum Turing machine down to the ordinary transition function of the classical Turing machine. Okay, that's probably enough information for one talk, at least for now. If people are interested, I might talk more about this later today or tomorrow if people want to find out more. But obviously there is another lecture that will cover more in more mathematical detail what what the correspondence is between things like multi-way evolution graphs and projective Hilbert spaces, and quite excitingly, how you can define an analog of general relativity that applies, whereas general relativity applies in the ordinary space-time causal network. If we consider the multi-way causal network, that is that parameterizes the causal relations not just between events on one branch of history, but between events on multiple branches of history, it turns out you can define an analog of the Einstein equations that acts in the multi-way causal network as well, and the analog of those Einstein equations. Well, I think as Stephen already kind of may have mentioned in his keynote speech, the rather exciting thing that we discovered was that where you get the classical Einstein-Hilbert action in the case of the ordinary space-time causal network, what you end up finding in the case of the multi-way causal network, instead of the Einstein-Hilbert action, you end up with the path integral action. And so the relativistic Lagrangian density that you see in general relativity gets replaced with the sort of quantum field theoretic Lagrangian density that one considers in things like particle physics. But I'm not going to go into detail about how we derive that now, so I might as well stop talking for a bit. And if people want to, we can. Well, if people have any questions, I'm happy to stick around and answer them. But otherwise, if you want to take a break before we do a discussion session later on, then we can do that.
I just had a quick question.
Yeah, go for it.
On this, I'm trying to understand with this completion theory about the collapse of the wave function. Yeah. Where does the stochastic part come in? So, I mean, the path, as I understand, like the path weights that you showed are analogous to the amplitude, the probability amplitudes, right?
Right.
And so, how does it follow that the eigenstate that the system collapses into is basically a probability distribution on the squared amplitudes of those pathways?
Right. Okay. So there are a couple of subtleties in that. So one of which is that this process of measurement is of course not a probabilistic process, as you notice. It's a completely deterministic algorithm. And so this interpretation so necessarily this is a purely deterministic interpretation of quantum mechanics. As I will try to describe, maybe if I have time later tomorrow, that obviously implies that in order to achieve a violation of Bell's inequalities, if we're maintaining determinism, then we either have to violate local realism, or we either have to violate realism, or we have to violate locality. So and it turns out that locality violation is a natural consequence of these models. So what happens is in the multi-way causal network, like I say, because you have connections between updating events that exist not just on one branch of history, but between branches of history, you're effectively connecting events that are not just spatially separated, but also branchially separated. The reason why that's interesting is because two events that are nearby in branchial space don't necessarily have to be nearby in physical space, right? Because just because a pair of events are sort of adjacent, branch-like adjacent with respect to the multi-way causal network, doesn't mean that they're going to be that the associated events will be space-like adjacent in the ordinary space-time causal network. So what that means is, in the multi-way causal network, you can get causal relationships between events that appear to be highly spatially non-local, and but nevertheless are branchially local, and so still they still satisfy some analog of a finite speed of light, but they're satisfying that condition with respect to branchial space, which corresponds essentially to a finite rate of entanglement between eigenstates. So that's the reason this doesn't answer your question. I wanted to preface it by saying that this is a fundamentally non-probabilistic model of quantum mechanics, but nevertheless achieves consistency with Bell's inequalities by essentially allowing for kind of massive non-locality as a consequence of having causal edges in the multi-way causal network that can connect events that are highly spatially separated. Okay. So, but then you do ask a very good question of, even if it's actually deterministic, how do you go about, quantum mechanics, even if you have a purely deterministic but non-local interpretation of quantum mechanics, it still looks non-deterministic because of the non-locality. How can we actually see that? That's a really good question. And basically what it has to do with, actually, maybe I can show a picture. So what it has to do with is the fact that even though the completion procedure is deterministic, it is dependent on the observer. It's dependent on the choice of reference frame. So if I share my screen again. Okay, so way back when we did the foliations of the multi-way evolution graph, like here. Okay, so this is one foliation. This is what, corresponding to one possible sequence of measurement events that an observer could perform, one possible sequence of events, of rewrite events that they could see. But we could consider an observer, and in fact we will in tomorrow's lecture consider observers who are who effectively have kind of like boosted foliations of a multi-way evolution graph where they see a different sequence of measurement events. And so that's important because the sequence of measurement events that the observer, or the sequence of states that exist on that branch-like hypersurface is the, sorry, it's not a sequence, it's an unordered set. The set of events that exist on that branch-like hypersurface determines which events the observer is seeing as being in superposition, which states the observer is seeing as being in superposition, which states the observer sees as being being the eigenstates that exist in that wave function. So then when the observer performs a measurement, those are the states which they're performing completions with respect to. What that means is if you had an observer which had a different, who was seeing a different collection of states in their branch-like hypersurfaces, they would perform a different completion procedure, because instead of attempting to collapse this branch pair that corresponds to AAB and ABA, they would be attempting to collapse this branch pair corresponding to AAB and ABB, which is not a branch pair with respect to this foliation, but would be a branch pair with respect to some tipped foliation where these two states were treated as being equivalent. So in other words, so even though the completion, once you have a foliation, the completion procedure is deterministic, but it's non-deterministic at the level of what your observer is. If you make a parameterized change of observer, which is like the analog of a Lorentz boost in the multi-way evolution graph, you will see a different eigenstate. You will see a different outcome of that measurement operation. And so the reason you get probabilities coming out is precisely, okay, it's deeply related to this averaging process that we had to do in the causal network. So you'll remember when we were doing the Einstein equation derivations in the causal network, to derive continuum equations, what we had to do is average out over all possible time-like projections, which is like averaging out over all possible choices of foliation, or all possible local gauge choices. To derive the path integral, we have to do exactly the same thing. We have to average out over all possible local observers, all possible choices of branch-like hypersurfaces. And so so when we do that, what we're doing is, you're averaging out over all possible completion procedures that you could have applied, and therefore all possible sort of eigenstates that you could have observed as the outcome to that measurement. And so what you get is something that looks statistical. It looks like the measurement process was probabilistic, but that's only that's only reflecting the fact that you're having to take an average over all possible observers. If you're a single observer, seeing a particular sequence of branch-like hypersurfaces, then everything about the measurement process is fully deterministic. So the stochasticity that you're alluding to arises precisely from the fact that there is the canonical observer. There isn't a canonical reference frame like a cosmological reference frame for the multi-way evolution graph. It's observer dependent, and the observer dependence is where the probabilistic nature of the measurement effectively comes from. I hope that answers your question. I can perhaps make a more precise version of that if you're interested, but that's the basic idea.
This is less a question about the material and more just kind of a request. Can you provide any resources on that Knuth-Bendix algorithm?
Yes, yeah. Okay, so sure. Yes, there are plenty. There's actually, I think Daniel. I don't know if Daniel Sanchez is here. Yes, he is. Daniel recommended in the physics chats, which I think is a great recommendation, this thing called term rewriting and that, or term rewriting and all that, which is a kind of a general reference book on a bunch of techniques and ideas and algorithms from abstract rewriting theory and term rewriting theory. And it's the place where I learned things about things like the Knuth-Bendix completion procedure. I will post a link to that. I will see if it's possible to get a PDF, and I'll post a link to that in the resources channel later on. But yeah,
I'll do it. I have a PDF.
Oh, you do? Okay.
Okay.
Daniel, yeah, have you already sent it in, or can you?
I will.
Perfect. Okay, awesome. Thank you so much.
I would also have a question.
Yeah.
Do you think that it could be somehow constructed. I mean, a measurement not just interpreted in a way, but also constructed some kind of structure in this system, which would actually make and behave like a measurement apparatus.
Yes. So that's something we've looked into, and again, if I have time, I might try and discuss that a little bit tomorrow. The basic answer, as with so many of these questions, is we haven't looked at it in as much detail as we would like. But the basic idea is, okay. In fact, Stephen might have a nice picture of this. So no, actually, I know he has a nice picture of it. Let me see if I can actually find it. So the basic idea is you can use kind of the analog of gravitational lensing to essentially force convergence of geodesics in the multi-way evolution graph, which is a slightly crazy sounding and abstract idea, but it's something that we're trying to make precise. And there we go, there it is. Okay, let me share my screen. So in Stephen's technical exposition, there's this example of a sort of one of these foliations of a multi-way evolution graph, which kind of freezes time around a particular collection of states. And actually, there's a better example. Okay, no, here's a better example. So here's a multi-way evolution graph where there is a normal form, and in which so in order to get around having that normal form there, you're essentially having to freeze time around that state, like you would for a space-time singularity in the causal network. So the idea would be that when you set up a piece of measurement apparatus, it's like you're setting up the analog of a black hole, but in multi-way in the branchial space, in the multi-way evolution graph, rather than in the causal network. So the reason why that would kind of actualize or mechanize this measurement process is essentially, so what would happen is if you had a singularity that was cloaked in some branchial event horizon, and it was effectively producing convergences of geodesics like you would get with gravitational lensing around around an ordinary space-time black hole. Well, the convergence of geodesics is essentially the convergence of branch pairs, right? Because a geodesic in the multi-way evolution graph is just a rewrite sequence. It's a sequence of updating events. And so if you have a pair of geodesics that would otherwise have diverged, but which now, because of the presence of that kind of branchial black hole, the presence of that singularity, are now forced to converge, that's like you're imposing a completion procedure. And so this notion that you can construct both physical and coordinate singularities in branchial space is our current sort of conjectural idea of how this measurement process is sort of actualized in these systems, but by some analog of gravitational lensing. But that's a process that we don't understand. It's still very much a sort of a hypothetical idea.
Maybe I'm getting this wrong, but doesn't it mean that the end of the measurement, the result of the measurement would depend actually on the updating event structure? So
what do you mean by?
I'm a bit confused. So confluence means that in some way the order of updatings is not relevant.
Yes, right.
However, if we have a black hole in a branchial space, doesn't it mean that it is actually relevant in that model?
Yes, absolutely. Because you're saying that branch terminates at a normal form, but other branches don't. Is that what you're saying? Yeah, no, I completely agree. So yeah, so definitely, I mean, having a normal form, if you have one branch that reaches a normal form and none of the other branches do, that's the minimal case of a system where you definitely can't have confluence. So yeah, if you had a branchial black hole that was kind of maintained and just stuck there as a normal form, then yes, absolutely, that would correspond to a global violation of confluence. The point is, in order to have effective confluence, you have to construct a foliation that avoids the presence of, like in ordinary spacetime, right? If you have the presence of a gravitational singularity, because because that gravitational singularity is just is a topological puncture in your manifold, any foliation that you construct in some initial value formulation of GR has to essentially avoid the presence of that singularity. You have to construct some reference frame, some foliation of the space-time that essentially avoids the presence of that singularity. What we're arguing is that you have to do the same thing, that if you want to have a system that doesn't depend on the details of the updating order, your foliation has to somehow avoid ever reaching the normal form. Because as you say, if you had a foliation that did reach the normal form, then immediately you violated confluence. But to construct a foliation that avoids the normal form is equivalent, we claim, to saying that you're applying a completion procedure. We have only kind of spotty heuristic evidence for actually stating that. We certainly don't have a formal proof of it, but that's the essential idea.
But doesn't it mean that then you want to avoid measurement?
No, because no, you want to avoid the measurement is what happens when you construct that foliation. The measurement is the set of equivalences you have to apply in order to avoid the whole system from terminating at that normal form.
Okay, I need to wrap around that my head still. Can't we say that basically this black hole formation in branchial space, this is basically can be interpreted as a many world interpretation if we don't take one branch, but we take all of the branches, then it's basically compatible with the many world interpretation.
Absolutely. It's this way of treating unitary evolution of branch-like hypersurfaces as being a multi-way evolution graph. That's very much a many worlds kind of story. It gives us a way of more precisely actualizing claims about interference between branches and measurements that collapse branches down than exists in the standard Everettian Deutschian model of the many worlds interpretation. But yes, absolutely, it's very much compatible. Oh, Nick, are you raising your hand? Is that?
Yeah. I have a question concerning measurement. So
Yeah.
does the requirement for observer to be effectively a large part of the hypergraph space assign some kind of limit on the size of those particle abstractions in it, so that they can perform measurements on each other?
Ooh, that's an interesting question. I don't know. I mean, it's such a wishy-washy heuristic claim that I made that it's hard to make any definitive statements. It almost certainly does. Yeah, I mean, knowing more about the measurement process will, as you say, undoubtedly will give us ways of estimating the effective length scale of discretization. It will give us ways of estimating the size of particles and the size of observers and so on in terms of elementary hyperedges. But we don't understand the measurement process. I mean, as is evident from the exchange with Joseph, we don't understand the measurement process in enough detail to be able to do that yet. It's the reason, the main reason for making this claim that the observer has to be macroscopic is, okay, this is gonna get a little bit weird and philosophical, but the sort of one intuition for kind of why that has to be the case is, the observer wants to construct a causal invariant representation of the world. They want to be not confused about which branch of history happened. They want to see a single thread of history. But in reality, there's this whole multi-way evolution. There's this whole multi-way system of possible histories. So how do they go about taking this multi-way system and reducing it down to something that, for them, they can represent in a causal invariant way? Well, the idea would be, in order for their model of the world to be causal invariant, at the very least, there has to be effective causal invariance within the observer itself. The observer has to perform a completion procedure, at least within their own local structure, in order to prevent themselves from being confused. And then the idea would be that if the observer is large enough, that the hypergraph structure of the observer constitutes like a sort of statistically significant sort of sample of the hypergraph structure of the rest of the universe, then the same completion rules that would cause the observer's wave function to collapse would also cause the rest of the universe's wave function to collapse. And therefore, it's meaningful to say that there is effective deterministic evolution of the universe. But like I say, that's a very hand-wavy, wishy-washy claim. But it's kind of the best we have at the moment. There is a more mathematically precise way of actualizing this measurement process in terms of collapsing events in branch-like hypersurfaces that doesn't require this assumption about the sort of macroscopic nature of the observer. But I just thought from a purely philosophical point of view, that was a nice way of thinking about kind of what the observer is and why the observer therefore enforces something like a completion procedure, why the observer enforces a coarse graining. So yeah, but that's a great question about using effective scales of the observer to estimate, scales of particle interactions and things. That's something I hadn't really thought about, but it's a neat idea. I don't think we're in a position to do it yet, but it's a nice thought.
Maybe still about this measurement process. So does it mean that from predictability point of view, this is a non-deterministic model from the point of view of an observer living inside this world?
Yes, yeah, I think so. I think because the observer can't know the kind of global gauge conditions for their own quantum reference frame, yes, I think it's correct to say therefore they can't know in detail what completion procedures they're actually performing, and so it wouldn't in principle be possible for them to predict what the outcome of a measurement would be. So yes, I think that's right. I think because in the same way as yeah, I mean, essentially for reasons of the equivalence principle, right? That just like in ordinary general relativity, right? You have the equivalence principle, which says you can't tell, you as an observer, just embedded within space-time, cannot tell the difference between a kind of an accelerating reference frame and a gravitational reference frame, or to be a bit more mathematically precise, what that means is you can't tell the difference between a pathology that exists in your own coordinatization of space-time and an actual geometrical pathology that exists in the space-time itself. And so I guess the analog of the equivalence principle here would say you can't tell the difference between, if you're seeing a particular sequence of branch-like hypersurfaces, you can't tell whether that sequence, which aspects of that sequence are determined by your choice of reference frame, and which aspects of that sequence are determined by the actual underlying geometry of branchial space. And the point is, in order to be able to predict the outcome of a measurement, you need to know what your own quantum reference frame is. And so the analog of the equivalence principle would imply that that effectively that information is observationally inaccessible to you. So I think that's true.
So can I think of this as being basically the same as just normal interpretation of quantum mechanics, but I'm using numpy.random to get a pseudo-random number every time I have to resolve an observation, and I just can't know the seed?
I guess, yeah, it's interesting. Yeah, so yeah, interpreting the details of the quantum observation frame as being the seed for some pseudo-random number generator is that's a nice way of thinking about it. I like that analogy. What the pseudo-random number generator is less clear. Whether it's the same as the pseudo-random number generator used in NumPy, but yeah, I think effectively that is a nice way of thinking about it. That's a nice analogy. Okay, were there any other, I mean, we have ostensibly a discussion session scheduled in like half an hour or something. So we can all come back and formulate some questions in breakout rooms and discuss them then. But did anyone, before we go and take a break for a little while, did anyone have any pressing issues they wanted to bring up?
Hey, Jonathan, not a physics issue, but
Yep.
Something about how to organize the discussions. So
yes,
yeah, what we did during the morning was, so we had so we created at least I did that. I think that Daniel also did that. So we started to threads in the physics channel for people to have the questions there, and you can see the questions. Then, so we were wondering if, so I was thinking that maybe we don't want to spam the physics channel with these threads, and maybe
agree.
having maybe having a channel just for the discussions, right? What do you guys think? I mean, in general, this is a question for the students. Are you comfortable with having a thread for your breakout rooms and having the questions there? Silence speaks a lot, so I will take that as a yes.
Like a physics Q&A? Something like that?
I guess, yeah.
Okay.
We're getting a couple of green votes from Luigi and Cameron.
Okay. Yeah, so I think I can create a channel. I have to, I still need to ask Vitaly about that. But I think for now, it's fine if we use the physics channel. Let's just create threads for every breakout room. How many breakout rooms did we have during the morning? 4, maybe? 5?
I think I made 5, but maybe we should make more. I mean, I don't know. I'm not sure how, I mean, my impression was that worked better than it did yesterday, but it still wasn't great. I don't know if that was the impression that other people had. But so do you think more breakout rooms is the solution, or fewer, or just less breakout room time, or how can we organize this better? Please, ideas.
All right, so let me see the schedule. So we have I think 30 minutes is a little too short for the discussion, especially if we only have, like, we have 5 breakout rooms, but we only have 1 Jonathan, right? Or do we have more Jonathans around there?
on different branches of the multi-way system, maybe.
Yeah. All right, so my suggestion will be to have the threads with the questions there. Like in the case in the room we had Joseph who also contribute to the discussion, but the questions that are unanswered can be also part of the Q&A. So that's more like the live streams, like when you read the questions and you answer the questions there with people in the audience. So I think we can try that.
Yeah, I mean, that sounds great to me. Are you sure you're okay to organize that? Is that something you can do?
Say again, sorry?
Are you sure you're able to organize that? That seems like, I don't want to place too much work on you.
Yeah, sure. I mean, yeah. I mean, I can make a thread for every breakout room. Just let me know how many rooms you're going to make, because I think if I'm not a host, I can't see how many rooms.
Oh yeah, okay. Actually, I should see if I can make you co-host when we do it again. That makes sense. Okay, no, I like that idea. And you think the idea? I mean, do people generally think the idea of just like collating questions and then feeding them back to me is that the optimal structure, or I mean, should we do it in a different way?
I feel like, so if we had like a channel, so just specifically for breakout rooms, so it would be like just hashtag breakout rooms, and then because the lectures are at different times, so then it would be organized that way. And then so all what you would have to do, Jonathan, if you were sitting in one breakout room, you could look at the other questions being discussed in different threads, which correspond to different breakout rooms. So then you could hop in between if you see something that you're interested in, or just to like see where the conversation is going in different breakout rooms.
That sounds fine to me, but I'm perfectly happy with that. But
I think we should have just a channel for the discussions, like like hash breakout rooms or something like that. I just want to double check with Vitaly before I do something I don't have to do on Slack. Yeah,
I'm sure he'll be okay with it.
Yeah, so like for now, I guess we can still use the physics channel. And I think the cool thing of having the threads and the questions there is that I suspect we may get very similar questions in some rooms. So we can then see what kind of questions are common between the audience.
I agree. Yeah. Okay. I mean, does anyone have any? Oh, sorry. Go on. Yeah.
Just what is my role precisely here?
Well, you can help run discussions.
Okay.
If that's okay with you.
That's okay with me. Just I want to highlight that I'm not an expert on the quantum side of the Wolfram model.
No, that's fine. You're just meant to be there as like the adult supervision for each breakout room.
Okay, maybe that's I can manage that.
and try and obviously try to guide discussion in interesting directions.
Yeah. Okay.
All right. So I guess everyone will take a break. Get back at 5.
Sounds good.
At the main room. You'll make the breakout rooms, and I'll just make a thread for every room.
Sounds awesome. Okay, we'll see how it goes.
All right.
All right. Thanks so much, everyone. All right, talk to you soon. Bye.